Welcome to the 46th lecture of second level algorithm course. In the last lecture, we have started proving the proof of correctness of Edmonds Blossom algorithm. So, let us finish that proof of correctness in this lecture. So, if you recall, Edmonds Blossom algorithm uses a subroutine which, given a matching M, either concludes whether it is a maximum cardinality matching or it outputs another matching M prime of same cardinality as M and an augmenting path, M prime augmenting path. Okay. So, it is enough to show the proof of correctness of that subroutine. So, the theorem in particular that we will prove is that Edmonds Blossom algorithm is correct. Proof. Enough to prove that or prove the correctness of the subroutine which takes a matching M as input and either outputs a matching M prime with cardinality of M prime being the same as the cardinality of M and an M prime augmenting path or concludes that the given matching M is a maximum cardinality matching. Okay, so this we prove by induction on the cardinality of M. The procedure is recursive that we have seen. So, base case if cardinality of M is 0, then every vertex is marked even at the beginning of the modified breadth first search. Hence, if the graph G has any edge, then an M augmenting path which is any edge in this case is returned by the algorithm. On the other hand, if the graph is an edgeless graph, then the current matching M, which is an empty matching, is clearly the maximum cardinality matching. Hence, if the input matching is an empty matching, then the subroutine outputs correctly. Now, the inductive step assume that the subroutine returns correct output for all input matchings M with cardinality at most k. We will prove correctness for all input matchings of cardinality at most k plus 1. Now, let us recall what was the algorithm doing. The algorithm was performing a breadth first search traversal, a modified breadth first search traversal, and it can either find an augmenting path or an blossom, or it reports that the current matching M is the maximum cardinality matching. So, in all three cases we will show that the algorithm is correct. If an M augmenting path is discovered during modified breadth first search, then the algorithm or the subroutine is clearly correct. This is so because if there exists an M augmenting path, then the current matching M cannot be a maximum cardinality matching. This we have proved before. And in this case, the subroutine is supposed to return another matching or a matching M prime of same cardinality as M and an M prime augmenting path. So, in this case, the matching M prime is the same as the matching M. So, this case is fine. Case 2, suppose the subroutine discovers a blossom during modified breadth first search. In this case, the subroutine replaces M with another matching M prime of same cardinality, so this is not blossom, this is in general it discovers a flower. To get rid of the stem of the flower. Okay, so it gets rid of that stem of the flower and it is left with the blossom. Then it calls itself recursively on graph G mod B with matching M mod B. Where B is the blossom that the subroutine has discovered. If the subroutine returns an M mod B augmenting path P in G mod B, then we have seen in the last lecture that we can compute an M augmenting path Q in G from P in polynomial time. Hence, in this case the algorithm or the subroutine is correct. On the other hand, if the subroutine returns that M mod B is a maximum cardinality matching in G mod B, which is correct by induction hypothesis then we have seen in the last lecture that M is also an M augmenting path M is also a maximum cardinality matching in G. Hence, the subroutine is correct in this case also. Now, the third case, the subroutine returns that M is a maximum cardinality matching because the Q has become empty. So, in this case, let us see how the modified breadth first search forest looks like. It starts with nodes marked even So, this is how a modified breadth first search tree may look like. Now, what are the edges of the graph? There are three types of edges in the graph. The first one are edges present in the modified breadth first search forest. The second one are edges discovered during the modified breadth first search, but because they are between even vertices and odd vertices, they were ignored. Edges discovered during modified breadth first search, but ignored because they are between vertices already marked even and odd. And the third type of edges are edges not discovered during modified breadth first search. Okay. So, how come those edges be there? For example, if a connected component of the graph is perfectly matched that means all the vertices are matched, then no edge in the in that connected component will be discovered during modified breadth first search. Okay. So, in the next lecture we will use these three types of edges to construct a set of vertices which proves that the current matching M is a maximum cardinality matching. Okay. So, let us stop here. Thank you.